Hello, I welcome you all in this presentation related with the subject failure analysis and prevention, and we will be talking about the failure analysis of the precipitation hardenable aluminum alloy components. And you know that the strength in these alloys is primarily imparted through the precipitation hardening heat treatment, and if the heat treatment is not done properly due to the inappropriate selection of the heat treatment process parameters, then we end up with the undesirable microstructure and so the mechanical properties, which in turn adversely affects the performance of the component during the service. Okay. So, initially in this presentation we will try to talk about the basic approach of the heat treatment and the principles related with that, precipitation hardening heat treatment of the common aluminum alloys, and then we will try to see how the heat treatment process parameters affect the microstructure and mechanical properties, and thereafter we will try to take up one case study related with the precipitation hardenable aluminum alloy component which failed prematurely, and so the investigation was undertaken to find out what led to the failure. Okay. So, let us say start with this presentation. So, we will be talking about first the what are the heat treatable aluminum alloys. Their aluminum alloys are classified based on the composition and also based on the way by which these are produced, like cast aluminum alloys and the wrought aluminum alloys. So, then in each category we have the heat treatable and non heat treatable aluminum alloys also. So, what are the common heat treatable aluminum alloys means which respond to the heat treatment with the change of microstructure and which in turn affects the mechanical properties. The need of the heat treatment of aluminum alloys, because the certain aluminum alloys in as cast condition do not offer the desired properties. So, when they are subjected to the precipitation hardening, then they result in the significant improvement. Apart from that, like many times the aluminum alloy component processed through the common manufacturing process like casting or forming or welding, then it is required to relieve the residual stresses. And so, stress relieving heat treatment may also be needed in these aluminum alloys, apart from controlling the microstructure to achieve the desired set of mechanical properties. So, what is the basic principle of the heat treatment and the common steps which are used in the two most common heat treatments like T4 and T6 for precipitation hardenable aluminum alloys. Then we will be taking up one case study on failure of the aluminum components due to the faulty heat treatment and the relevant findings and the observations. So, as far as the heat treatable aluminum alloy is concerned, so let us see that this list what it shows that this is the classification of the wrought aluminum alloys, okay, which is most commonly used. Cast aluminum alloys are used for a selected category, selected applications. Okay. So, the wrought aluminum alloys like the 1000 series is used for the pure aluminum, okay, having the aluminum more than 99% or more. The 2000 series aluminum alloys are dedicated to the aluminum copper alloys, which may have other alloying elements like aluminum, copper and magnesium. Okay. Then 3000 series is for aluminum magnesium alloys. 4000 series is basically the cast aluminum alloy series, which is preferably used for making the components through the casting route. Okay. So, but these aluminum silicon alloys can have the copper and magnesium, and when these elements are added, these make the cast aluminum silicon alloy also heat treatable. Okay. They respond to the heat treatment. Then 5000 series is basically the aluminum magnesium manganese alloy, having the aluminum magnesium and manganese. These are basically work hardenable aluminum alloys. Okay. Work hardenable aluminum alloys. 6000 series having the aluminum magnesium silicon, these are the heat treatable aluminum alloys, and the aluminum 7000 series is also heat treatable aluminum alloy series. So, though those which are rated, so 8000 series is dedicated for aluminum with the other elements like aluminum, lithium, and likewise 9000 series is unused. So, if you see here, those which are highlighted in red, these are heat treatable aluminum alloys. And even in case of the 4000 series aluminum alloy, when we have copper and magnesium, then these also respond to the heat treatment. So, these all can also be classified as a heat treatable aluminum alloy, especially when the in the presence of these two alloying elements. Okay. So, this is about the the entire classification of the wrought aluminum alloys, and the most common heat treatable aluminum alloys are like aluminum, copper, magnesium, that is 2000 series, and these are the two most common aluminum alloys like 2024 and 2014. Similarly, aluminum, magnesium and silicon, this is a 6000 series aluminum alloy, and in this series we have 6061 is one of the most commonly used aluminum alloy, and 6063. Similarly, in aluminum, zinc, magnesium, aluminum alloys, we have the two most common, it is a 7000 series and having like 7075 and 7039. These are the other two common aluminum alloy of the aluminum, zinc, magnesium series. Most of these heat treatable aluminum alloy offer the advantage of the high strength to weight ratio. So, because of this feature, these are extensively used in automotive and fabricating or manufacturing the aircraft component, where light weighting is important. Okay. In automobile sector and in aircrafts, where the light weight is important for increasing the fuel efficiency, increasing the payload, the weight is important. So, the structural members are made of the heat treatable aluminum alloys like 2024, 6061, 7075. Okay. And these heat treatable aluminum alloys, if are given proper heat treatment, then the strength offered by them is extremely well. So, what is the basic principle of the precipitation hardening aluminum alloys is this, like say this is the regular matrix of the of the aluminum. Okay. Say it is having few incomplete plane of atoms like dislocations, okay, here and there. So, in these incomplete plane of atoms move under the externally applied stresses easily, and which in turn result in the deformation. These incomplete plane of atom is called dislocations. So, how easily dislocations are able to move, that in turn results the plastic deformation. Eventually, the dislocation movement resulting in the plastic deformation, and how easily it is happening, that will determine the strength or yield strength of the material. So, if the dislocation movement is resisted, then the stress required to cause the plastic deformation increases, and that is what is achieved through the development of fine precipitates. So, when these fine precipitates come across the moving dislocation, the movement of dislocations is resisted, and that in turn increases the yield strength. And that is why what we say, basically we try to realize the fine precipitates, fine well distributed precipitates. So, in the matrix, if the fine well distributed precipitates are present, then these will frequently be coming across the moving dislocations to enhance the yield strength. Okay. This is the mechanism of the precipitation hardening. Okay. So, if the size of these precipitates increases, then this reduces the yield strength. In pH precipitation hardening aluminum alloys, if we, due to one or other reason, if we get coarse precipitates, then this will be reducing the yield strength and hardness. Okay. So, efforts are always made to produce the fine precipitates, okay, for peak hardening and higher yield strength. Another possibility is that these precipitates are localized, say these precipitates are localized only at the grain boundary. Okay. Then these will not be causing segregated precipitates will also not be causing much of the increase in yield strength. So, the well distributed and fine precipitates actually help in improving the yield strength and hardness significantly. So, how it is realized? So, for that we follow a typical heat treatment cycle, which involves heating first to the high temperature, okay, then holding at that temperature for some time, okay, and then again quenching very rapidly, okay. Then after quenching it at low temperature, again it is reheated, and then it is kept at that temperature for some time, followed by normal air cooling. Okay. So, these are the steps. So, the first step, where heating to the high temperature, this is called solutionizing temperature. Idea behind this is, let us heat the aluminum alloys to the high temperature, precipitation hardening aluminum alloys to the high temperature, so that the homogeneous solid solution of that aluminum alloy can be made. Okay. So, if there are alloying elements, they will get dissolved and they will form the homogeneous solid solution. And how long it is to be kept? So, this the holding time or soaking time, you can say as a solutionizing time. Solutionizing time. This again will depend upon the size of component and the grain size. The components made by the casting process, they need longer solutionizing time as compared to those which are made by the wrought, means the deformation based approaches, that will be, because that will be offering the finer grain structure. So, if the component being subjected to the precipitation hardening, if it is having fine grain structure, then it will take shorter time to form the homogeneous solid solution as compared to the case when the structure is coarse, that will need longer time. So, once we have got the homogeneous solid solution, it is subjected to the next step, that is quenching. So, this quenching results in the supersaturated solid solution. Supersaturated solid solution means alloying elements which are present in the matrix in the homogeneous austenitic state at a high temperature, when they are subjected to the rapid cooling, they get trapped, they do not get time to diffuse out, even if their solubility is less than the maximum solubility that they can accommodate. Okay. That is why they result in the supersaturated solid solution. Once the supersaturated solid solution is formed, then on reheating again for the aging purpose, these alloying elements which were supersaturated, these starts appearing as a precipitates. Okay. So, aging happens in two ways. Aging can be done even at the room temperature, that will be termed as a natural aging, and if the reheating is done to the high temperature, then it will be termed as artificial aging. Artificial aging takes a shorter time, maybe 2 to 6 hours or 8 hours, but natural aging may take longer time, maybe like 24 hours or 7 days, like that. So, natural aging takes longer time to develop the precipitates and achieve the desired maximum strength, but artificial aging, since it happens at a higher temperature, so greater diffusion activity will be leading to the quick precipitates desired for hardening purpose. Okay. So, these are the three steps. One is the solutionizing, then quenching, and then aging. Aging can be artificial or it can be natural. So, this is what happens, like say in the phase diagram we can understand this. So, this is a one for typical aluminum copper alloy. In x axis it is showing the copper content, in y axis it is showing the temperature. This particular line is the Solvus line, which indicates the solubility of copper in aluminum as a function of temperature. Okay. So, what we do, say this is a particular aluminum copper alloy. When it is heated, then at this temperature it will be completely saturated with this kind of the aluminum, with this kind of copper content. On further heating, it will be completely dissolving and will be forming the homogeneous solid solution. Okay. And so, you will be having basically alpha aluminum with the dissolved copper. Okay. Once the homogeneous solid solution of the aluminum copper is formed, we do the rapid cooling again back to the room temperature. This is called quenching. On quenching, we form the supersaturated solid solution. Okay. So, the first, the aluminum copper alloy is heated, we get the solid solution, and then on quenching we get the supersaturated solid solution. And when during the aging, what happens that these three different alloys will be forming the three different types of the precipitates. Okay. So, aluminum copper alloy during the aging, what it after quenching during the aging, it will be resulting in GP zone formation, and then the aluminum copper magnesium phase, the S dash and S phases, and then aluminum magnesium silicon phase, that is the beta dash and beta phase, and aluminum zinc magnesium gamma dash and gamma precipitates. Okay. These precipitates are supposed to contribute towards the strength. So, depending upon the alloy composition during the aging, the different types of the precipitates will be developed. Okay. So, if we see this, this Solves line can be used for different alloy compositions. It will indicate how much heating should be done. So, basically the phase diagram, okay, phase diagram of that aluminum and that particular alloy, okay, use its phase diagram to identify how much temperature it needs to form the homogeneous solid solution, and above that we try to heat. So, for this composition will be heat, this is the Solves line, then above this we will be selecting say 30-40 degree centigrade higher than that temperature for solutionizing purpose. Higher the temperature, rapid will be the solutionizing, shorter time it will take. Okay. Then it will be quenched simply to form the supersaturated solid solution. Thereafter reheating can be done, or there cannot be any heated depending upon the alloying elements. Say aluminum copper magnesium and aluminum magnesium silicon alloy, these are usually subjected to the artificial aging, but aluminum zinc magnesium also responds very nicely and very quickly to the natural aging, which means the aluminum zinc magnesium alloy can simply be subjected to the solutionizing, rapid cooling, followed by putting at the room temperature so that it is naturally aged. Okay. So, depending upon the alloy composition, we can use the natural aging or the artificial aging. So, these are the steps related to the precipitation hardening heat treatment. Okay. This is what it shows that what happens during the aging. Okay. So, this diagram will more clearly show like when we use the low temperature for aging, there is an increase in hardness is very gradual. It takes long actually. So, this may be in days or weeks to achieve the desired strength. Okay, at low temperature, this is 30, 40, 50, 100 degrees centigrade. But when we use high temperature, aging happens very quickly. Okay, and then it will be reaching to the peak hardness level rapidly when we use the higher temperature for aging. Okay. So, this is one aspect. This diagram shows the two things. One is the aging must be done for the optimum time depending upon the temperature. Okay. If we use low temperature for artificial aging, it takes long to get the maximum hardness and strength, while if the high temperature is used for artificial aging, then it takes less time. Okay. But for each aging temperature, there is a specific value of the aging time corresponding to the peak hardness or peak strength. Okay. Either side of that, like if the aging time is less for a given temperature, then strength and hardness will be low, and if the aging time is longer, again the strength starts decreasing. Okay. So, the conditions of temperature and time corresponding to the maximum strength, that is called peak hardening, is to be identified and established. If it is not so, due to any reason, if it is underaged or overaged, then strength that will be getting, that will be reduced. Okay. So, this will be happening in both the cases, whether we use low temperature or high temperature aging. Okay. This is the underaged situation, this is the overaged situation, and both over and underaged will be leading to the reduced strength. Why? Because when we use underaging conditions, then our precipitation is incomplete, means we do not produce enough precipitates. And on the other hand, when we use the conditions corresponding to the overaging, means there will be coarsening of precipitates and grains. So, this coarsening of precipitate and grain again starts compromising the hardness and strength. That is why it is very important to use the optimum time for given aging temperature for peak hardness. How the hardness and strength is imparted, that is what we can see in the axis. In the x-axis we have aging time and hardness in y-axis. So, initially the GP zones contribute towards the strength, Guinier, Preston. These are the kind of phases which are precipitates which are formed in the beginning. These are very fine, okay. And then the GP2 zone is formed, and then we achieve the peak hardness at say 130 degree centigrade for aluminum copper alloys, and then we get the condition of overaging. When we use the higher temperature of aging, again we get the increasing the peak hardness is achieved earlier and then overaging starts. Okay. So, it is important that aging is done, especially artificial aging is done for optimum combination of the aging temperature and time. Both under and over aging will result in the reduced strength of the aluminum alloy subjected to the precipitation hardening. Aluminium copper magnesium alloy, this is one of the most common series of the precipitation hardenable aluminum alloys, which is used extensively for making the aircraft components and also wherever the weight is extremely important. So, for having the high strength to weight ratio. So, because of its good corrosion resistance and good strength, so these are extensively used. So, these are the few common alloys related with the 2000 series aluminum alloy like 2014, 2024, 2036, 2028, 2008 and 2010. So, what these alloys say that say the 2014 will have the higher composition of the copper and lower of the magnesium, but on the other hand 2024 will have higher copper and higher concentration of the Mg as well. For other aluminum, copper, magnesium alloys, these constituent of proportion or weight percentage of these elements, copper and the magnesium is lower, and accordingly, so this suggests the magnesium, the ranges of magnesium and copper content in common aluminum copper alloys 2036, 2008 and 2010, apart from like 2014 and 2024. Okay. We will be taking up one case study related to this aluminum alloy, that is why I talked little more. So, 2014 is one of the typical aluminum copper alloy, say having the higher concentration of the copper and lesser concentration of the magnesium, and what it shows the fine precipitates, okay, in the matrix of the aluminum, and what it shows the different aluminum grains. Okay. So, we can see that aluminum grains are there and with the fine precipitates of aluminum and copper. So, that is evident also from the this X-ray diffraction analysis of the 2014 aluminum alloy, and typical strength of the this alloy is like say 407 is the ultimate strength, 358 is the yield strength, and ductility in terms of percentage elongation is 10.21. So, this is reasonably good strength and the ductility metal. What happens when these alloys are subjected to the heat treatment? So, that is what we can see when the aluminum, silicon and the Mg alloy subjected to the casting, which kind of a structure we get. So, these are the like say the 4 different types of the microstructures. This is for the very low silicon content, 4% silicon, 8% silicon, 12% silicon, and then we have 16% silicon and 20% silicon. What it is showing that when the content of silicon is less than the eutectic, then it is termed as the hypoeutectic aluminum silicon alloy, and it primarily has the alpha aluminum with the eutectic mixture of aluminum and silicon at the grain boundaries. Okay. So, with the increasing silicon, the proportion of the eutectic is increasing. That is what we can see here, okay, 4 to 8 and 8 to 12. Up to this, the eutectic proportion is increasing and alpha aluminum proportion is decreasing. On further increasing the silicon content beyond the eutectic composition, means that is the hyper eutectic system, hyper eutectic aluminum silicon alloy, what we get? Presence of the additional phases in form of the primary silicon particles in the matrix of the alpha aluminum and eutectic mixture. So, in the hyper eutectic aluminum alloys, we have alpha aluminum, we have primary silicon and we have eutectic. So, these three constituents, while in case of the hypoeutectic systems, basically we have alpha aluminum in hypoeutectic and eutectic only. There is no primary silicon for eutectic, hypoeutectic systems. So, that is the case of this 1, 2 and also in 3. This is the eutectic or hypoeutectic aluminum silicon alloy. Okay, this is one aspect, that how the constituents change with the change of silicon content. Okay. Apart from that, what we can see in all these cases, we see the dendritic structure, dendrites of the alpha aluminum alloy. Okay. And in the interdendritic region, we have the eutectic mixture in the interdendritic. So, this dark phase that is in the interdendritic zone is basically the eutectic mixture. Okay. So, this is a typical cast structure thing, but when this alloy is subjected to the T6 heat treatment, means it is exposed to the solutionizing followed by quenching and then aging. So, artificial aging basically, because this is T6. So, what it results? All eutectic silicon is broken down, eutectic is broken down into the fine spherical shape mixture. Dendritic structure is also broken down and we have the aluminum matrix. Okay. So, what is happening? After the heat treatment, there is a complete modification. We get the aluminum matrix and fine spherical shape eutectic silicon particles, which are well distributed. So, this modification is expected to enhance the hardness, enhance the strength and also ductility. Okay. So, what it shows, that increasing the solutionizing temperature basically increases the, you see, as compared to the as cast system, it results in the higher hardness. This is one, this is attributed to the precipitation hardening. And also within, for a given heat solutionizing temperature, increasing solutionizing temperature increases the hardness, and as compared to the cast aluminum alloy also you will compare, then you will get the higher hardness. For a given solutionizing temperature, if we try to see the increase effect of the silicon content, then this will also show that the hardness is increasing in each band. Increase of silicon content increases the hardness, and increasing solutionizing temperature also increases the hardness because of the effective solutionizing followed by precipitation hardening. Similarly, as compared to the like say as compared to the as cast system, that is this blank, the hardness is lowest. Okay, but certainly it is increasing with the silicon content. On the other hand, if we do the aging at the different temperatures, then the effectiveness of the aging increases and we get the more effective strain precipitation hardening, and therefore, we get the increasing hardness with the increasing aging temperature. Okay. So, this is what is reflected also in strength, not just in hardness. For any alloy, increasing the solutionizing temperature increases the strength. Okay. Similarly, increasing the aging temperature also increases the strength for each category of the aluminum alloy, except this for the higher level. Okay. For this hyper eutectic. In eutectic systems, there is a continuous increase of the strength. So, now we will take up one case study. Here in this case study, what we will try to see, like a phylletosis of the bike component, which is made of the precipitation hardenable aluminum alloy. It is a structural members which takes the load during the operation, during the use. And this component of the bike failed prematurely within 6 months of service. So, when investigation was undertaken, and investigation revealed that material composition is as specified. So, there is no problem as far as the material composition is concerned. Design is also checked and it was found that it is as per the recommendation. So, that part is also clear. Visual examination of the failed component showed that the fracture occurred from the section where there was a change of cross section. So, obviously, there would have been a fillet or some kind of the, when there is a change of cross section. So, obviously, the stresses tend to get localized in that zone. Mechanical property studies showed the lower yield strength of 340 as compared to the specified one 400. So, what it is suggesting that material is of the lower yield strength than the specified one. Microstructure on the other hand revealed the coarse grain structure and coarse precipitates. So, this is indicating the possibility of the overaging of heat treatable or heat treated aluminium 2014 aluminium alloy. Okay. So, because overaging means the lower strength than the specified one. Coarse grains and coarse precipitates suggest the possibility of the overaging, and no defect whatsoever was found during the NDT. So, this suggests that there is no such problem of the soundness of the component. Of course, there would have been some stress regions and stress concentration due to the section where change in cross section was taking place, and that promoted or triggered the fracture, okay, due to the weakness, due to the lower yield strength of the material. Further investigation suggested the normal operation, no abnormal operation or no repairs, whatever it would have been of that structural member. Maintenance in this case was not applicable because this was a structural member of simple by. Stereoscopy and SAM suggested the dimple fracture with the significant deformation. So, means material is ductile, but of the lower yield strength, and that is why it showed the dimple fracture. And when the strength was compared with the new one, it was found that strength is actually lower than as compared to the new one, which is still not in use, or those which have been doing very well for long. So, when all these observations were analyzed, it was found that aluminum component failed due to the improper heat treatment, due to the overaging, which could be primarily due to the like say improper aging conditions that resulted in the lower strength due to the coarse grain structure. So, far as the possible recommendations are concerned, like say implement the suitable design changes in the area where the stress localization is expected to be taking place, because the failure occurred from the section where there was a change of cross section. So, give the proper fillet or relocate or redesign in such a way that the stress localization does not happen there. Also ensure that proper strength is achieved through the proper optimization or establishment of the T6 heat treatment, because this suggested the possibility of the overaging, as it was apparent from the coarse grain of the alpha aluminum and coarse precipitates that resulted in the lower strength, and which in turn resulted the fracture of the component. So, that is all in the today's presentation. I will summarize this presentation. In this presentation, basically I have talked about the common heat treatable aluminum alloys, what is the underlying principle of the precipitation hardening, and what are the important parameters related to the precipitation hardening and how those are designed and optimized. And then we have taken up one case study related with the bike component made of the precipitation hardenable aluminum alloy 2014, and what led to the failure that was established. Thank you for your attention.